Okay, thank you very much. Well, it's a huge regret that I'm unable to join you in person in Tromsø, right? As Didier was telling me that it's lovely, right, in where you are, right? So I hope you enjoy the location as well as the conference, right? So without further ado, I'm gonna go into my talk, right? It's unfortunately I'm probably not gonna be able to finish everything, but at least what I'm gonna do is I hope to give you a flavor of tensor networks in my perspective, right? And you're gonna learn more about it in the next couple of talks today. Okay, so I should say this is the research part of this talk. There are a couple of sort of new perspective, right? That's joined with my former postdoc career, right? Now at Chinese Academy of Sciences, right? All right. So let me so the thing is, of course, tensor networks has to do with they have to do with tensors, right? And presumably by now you already know what that is. But so in my, I'm just going to give you my own take, okay? My take is very simple, right? Tensors are important because they capture three ideas, okay? Equivariance, multilinearity, and separability, okay? And today we're going to focus on the last one, right? The notion of separability, okay? And uh, that is going to lead us to the method of separation of variables. Presumably, you learn about that in calculus. That's probably the first method, and that you learn, when you studied PDEs. Okay. There's also going to be a little bit of multilinearity, right? In a sense of at the end, I'm going to talk about something called. I'm going to address the question: when can a PDE be solved using separation of variables? Okay. Well, it's an important question, right? And the answer to that turns out to be, it depends on something called the Ricci curvature tensor. You might have heard of that. And also the Riemannian metric tensor. You surely have heard of that. And so these tensors typically are defined in the second way, okay? The multilinearity, okay? Yeah, so the thing is, you can view them as kind of equivalent. There are three sides of a three-sided coin. I've never seen that before, but I know we don't have that in the US. You probably have that in Europe, right? Found a picture of that on the web, and it's a $1 euro coin. Okay, so I'm gonna say a word about that last point. Okay, yeah, actually, the thing is, I forgot it. Right, ultimately, my way of introducing tensor networks is that it's simply an extension of the technique of separation of variables. Okay, that first technique that you learn in calculus about solving for solving PDE. Okay, now let me say a word about that last point. Okay, in case I don't get to this part I might miss because this is like right at the very end. So whether you can apply separation of variables, right? Of course, in your class on in your calculus class when you learn how to solve PDE, typically what you're given is that you're given an equation, right? And you're taught that if I apply that technique, if I assume that my solution is separable, meaning I can write it as a product of univariate functions, right? Depending on the different variables, then suddenly magically that problem separates into multiple ODEs. Okay, and presumably you have already learned about ODE, so you know how to solve the ODE. But that's not always the case. Okay, if I give you like let's say the equation on the right, okay, the PDE on the right. Right, it's actually the same PDE as the one on the left. It's the wave equation, okay, except I changed the coordinates. And it's a very simple change of coordinates. It's a linear change of coordinates, right? So suddenly, if you apply that technique, you cannot get a solution anymore, okay? If I plug in F equals to phi of xi and xi of eta, right? You cannot solve it anymore. So the moral here, okay, is that this whether you can apply separation of variables or not ultimately depends on the coordinates, depends on the choice of your coordinates. Okay, and this is where what I said about the metric tensor and the Ricci tensor comes in. Okay, that's going to help you decide whether the coordinates you're working in allows you to use separation of variables. Okay. And of course, the relation of all this to tensor network is that ultimately tensor networks is, well, are, right, in my opinion, right, just an extension of this technique of separation of variables. So it actually generates a lot of unanswered questions that I hope will be of interest to the participants. Okay. Okay, so let me remind you of this very basic technique that you learn in calculus, well, separation of variables, except that now I'm going to formulate this entirely in terms of tensors. Okay. It's now going to be entirely in terms of tensors. Okay, so now let me start from the beginning so that I can connect it to what you are familiar with. First of all, I'm going to define something called a separable function. So what's a separable function? Now let's say I have a function of d variables. Now these d variables can be scalar variables, they can be vector variables, they can be discrete variables. It doesn't really matter. Okay, x1 to xd. Okay, x1 to xd can be vectors, can be categorical, can be natural numbers, can be scalars. It doesn't really matter. Okay, all that matters is that the function, right, is real or complex value. It takes value in a field. Okay, now the thing is the well, what do you mean by separable, right? You have actually two, but equivalent notions of writing down a separable function. One is additive separable, okay? If I can write a function in d variables as a sum of function each depending on just one of the variables, this is called an additively separable function, okay? Well, this is not the one that you learn in the when you learn how to solve a PDE. The one that you learn is typically multiplicative separability. Okay, that is if I can write it as a product of functions, each depending on one of the variables. Now, actually, they're equivalent. Okay, well, one way to see it is that taking exponent, right, exponentiating the additive separable function makes it into a multiplicatively separable function. Taking log of a multiplicatively separable function, transform it into an additively separable function. Okay, and both notions are important, right? We want to use like both, okay, right? But we'll focus on the second one. An example of the first one, right? Well, since Didier is my chair, well, I cannot help mentioning this. Well, his specialty is convex optimization. He's a world expert on that, okay? Well, so there's this misconception that a convex optimization problem can be solved in polynomial time. Okay, that's nonsense. Okay, there are a lot of convex optimization problems that are NP hard. Okay, but one convex optimization problem that can be solved in polynomial time is what's called a separable convex optimization problem. That means the objective function can be written in the first form, okay? In this form here, okay, as an additively separable function. In fact, if you have a convex function, right, f1 to fd, if they are all convex and you can write it in this additive separable form, then this convex optimization problem can be solved in the same time complexity as linear programming, okay? Linear programming is a special case of this. Okay, so this is, of course, unrelated to what I'm going to talk about today. I'm going to be talking about PDE, but I just want to let you know that separability is, well, it arises in every area of mathematics. Okay. Now, okay, so let's look at some examples. Okay, so this is going to sort of illustrate what I just said. Okay, like so we now look at statistics and we now look at mathematical physics, right? And you see that separable functions, right? In this case, multiplicatively separable functions abound. Okay. Well, the most standard example, right, in quantum mechanics, it's the quantum harmonic oscillator. In fact, some people say that all physics is just a way to describe the to apply an approximation that is the harmonic oscillator, right? So this is what is the this is essentially just think of it the wave function, right, of a spinless particle subject to isotropic potential, right? The wave function, right, if you write it in, if it can be solved in closed form, it takes a form that is multiplicatively separable, right? It's hm, hn, hp. These are your univariate emit functions, right? And this, of course, is an exponent, okay, of something that is additively separable. And like I said earlier, when you take when you exponentiate an additively separable function, what you get? Well, it splits into products of exponents. Okay, in this case, product of Gaussian, right? So the same thing is true, right? If you look at like any Gaussian in general, right? If you look at any Gaussian in general, what at first glance is not going to be separable, but you can always diagonalize the quadratic term, okay? In which case it becomes look at the eigen coordinates given by the eigenvectors, and then suddenly it becomes exponent of an additively separable function, and therefore that function is multiplicatively separable. Okay, now the thing is, so now this comes up in statistics and a variety of other areas. I'm not going to go too much into it. But anyway, right, this can be written in the form of tensors. In fact, you can use this to define tensors. Okay, now the thing, right, is that, to a first approximation, right, any vector space, right, you can regard it as a space of, or let's say complex vector space, right, for simplicity. Any vector space is just the set of complex valued function on some set. Okay, now if that set, right, if your omega I, that set happens to be discrete, right, finite, if it's a finite set, then you get a finite dimensional vector space. If it's infinite or if it's a continuum, then you get, like a infinite dimensional vector space. Okay, so in my world, right, at least for the purpose of this talk, vector space is very simple. A vector space is simply the set of all complex value function on some domain. Okay. Now the thing is, what is a tensor product of vector spaces? Okay. Now the tensor product of vector spaces is simply the sum of all multiplicatively separable functions. That's it. Okay. Now, what is a multiplicatively separable function? Right, we saw it earlier. That's just a product of function, each depending on one variable, right? So the variables are do not interact, okay, so to speak, right? So x1 and x2, they do not share any coordinates, okay? Now, if I take the product, well, I can take product, right? Because each of this is a complex number. So these are all complex value. If I take the product, this operation is going to be called tensor product, okay? This is called a tensor product of functions, right? So this defines a separable function. So what is a separable function? It is a rank 1 tensor, okay? Well, so I believe most of you know about this. So what is the tensor product of vector spaces? Is simply the set of all functions that can be written as a sum, a finite sum of separable functions, okay? So by definition, this defines tensor product. Tensor product is simply the set of all finite rank. Tensor product of vector spaces is simply the set of all finite rank tensors, okay? Now the finite is very important, okay? Now the thing is, if it's infinite dimensional, then you have to take closure and infinite. Well, okay, but we won't go there, okay? So everything is going to be finite, right? All sums are going to be finite in this talk. Now, if you define tensor products on the vectors, okay, then you automatically get tensor products on the operators on this vector spaces, okay? Now, this property is very important. This is called functorial, okay? This is the functoriality. Well, I didn't use that term in my slides, but that's essentially saying that the tensor product is a functorial construct, okay? Now, if so the thing is, how can I define tensor product of operators, right? I'm going to just use the tensor product of vectors to define tensor product of operators, okay? If I have linear operators, okay, phi1 to phi d, right, acting on different spaces, different vector spaces, right, taking values in other different vector spaces, then the tensor product of this linear operator, right, is defined on a rank 1 tensor or a tensor product of vectors in this manner, right? Just take the image of each and take the tensor product for everything, right? And extend this linearly to the entire tensor product space, okay? The tensor product V1 to Vd. Now I get this second space should be, let's forget about W1 to WD. Let's assume that, the domain and the codomain are identical, okay? Now, the thing is, what about a separable operator? Now, it turns out that an operator that looks like this, you might think that this is the definition of a separable operator, Now the terminology is a little bit different here, okay? A separable operator is going to be different. It's going to be this operator instead, okay? That means I'm going to take the first operator and I'm going to tensor it with identity everywhere, okay? Else, okay? And I'm going to do the same thing for the second operator, v2, and we're going to tensor it, replace the other copies by all identity operators, and I'm going to do that. Now, what is this? This is actually, well, if you learn about, if you have taken a class on calculus, where you learn about Leibniz rule or product rule for differentiating functions, right? You know, this is essentially that. Okay, this is Leibniz rule for tensor product. Okay, so what I'm showing you here is, roughly speaking, it's the first order Taylor expansion of this thing. Okay, okay. So, well, and an operator that looks like this, right? And this is always going to be linear, right? Is going to be called, because it's, well, you know, the first order Taylor expansion. Anything that's first order Taylor expansion is linear. Okay, so this is what's called a separable operator. Okay. Now, okay, so now I'm going to present to you my version of separation of variables, and you're going to see that it's actually identical to what you have learned in calculus. Now, if I give you a separable operator, okay, that according to a previous slide, then separation of variable is the technique that transform the homogeneous linear system, okay, phi is a linear operator, right, x on, well, this vector, right, this solution of this form equals 0. This system can be transformed into a collection of d eigenvalue problems. Okay, the right-hand side here, these are all eigenvalue problems. Okay, phi of phi equals lambda times v. Okay, this are, and phi are linear operators, so these are all eigenvalue problems. Okay, so instead of a large system of homogeneous equations, linear equations, I have broken it all into pieces, decoupled it into pieces. But each of it is now an eigenvalue problem instead of, well, a linear system. Okay, so this is the abstraction of the technique of separation of variables. You take a tensor equation, right, involving tensor product of operators and tensor product of vectors, and transform it into eigenvalue problems. Okay. Okay, good. So how do you prove this? How do you prove that? What is this arrow here? This arrow here is actually very simple. Okay, it relies on just one very simple fact. It relies on this fact here. Okay, if I take, well, this is a property of tensor product, right? If I take any two non-zero vectors, I take their tensor product, and it's equals to the product of another two non-zero vectors, v prime and w prime, then you must have v equals to some scalar times v prime, and w equals to exactly the reciprocal of that scalar times w prime. Okay, so this is almost like a tautology. Okay, okay, it's a very simple fact, right? And if you apply this fact constantly, you're gonna get this. You're gonna get this arrow. Okay, you're gonna get this arrow here, and that allows you to decouple a system of homogeneous linear equations into a collection of eigenvalue problems. Okay, and this, well, I'll let you stare at it for a while I take a sip of coffee. This is separation of variables. Okay, now so this fact here, by the way, you know, if you recall what you learned in calculus, right? You know, you take a PDE, right? You know, in X and a PDE, well, you know, in X and Y, right? So you're gonna, when you apply separation of variable, you're gonna get like a function of X equals to function of Y, and therefore you're gonna say, oh, they must be constant, right? Because you cannot have a function of X equals a function of Y if they are both non-constant. So they must each be equals to a constant. Okay, that trick is exactly what I'm writing down here. Okay, that is this. Okay. Okay, now, okay, so let's do d equals 3. Okay, this is the only proof I'm going to show you in my entire talk. Okay, well, so just get rid of the indices, right? You know, if I have this operator, phi, xi, and theta, okay, phi is going to act on, well, you know, the vector space u, right? You know, xi is going to act on the vector space v, and theta is going to act on the vector space w. Okay. Now, if I have this equation, right, it's a homogeneous system of linear equations, right? Okay, and is equals to 0 on the right. Now, so the thing is, I'm gonna use the definition, write it out, right? And I'm now gonna use the trick, right? So I have some vector, right, in the U vector space times a vector in V tensor W, right? The vector space V tensor W equals to this, okay? Right? I'm just rearranging this equation, right? Right, pushing this term to the right. Well, by that easy observation, right, that must mean that phi of u must be equals to lambda of u. V tensor W is equals to 1 over lambda times whatever term this is. Now, the thing is that I'm going to apply the same trick again. Now this is now already in a form that I need. Now I'm going to apply the same trick to the second equation, okay? Okay. Oops, sorry about that. Okay. Okay, I'm going to apply it to the second equation, right? This same trick, and voila, I'm going to get what I need. And observe that the eigenvalues have the property that if you add all of them, it sums up to 0, right? As you would expect, okay, because it's a homogeneous equation. Okay, so this is the proof. Okay, this is the proof of this arrow here. Okay, you just add more variables. Okay, so now let's look at the wave equation that we saw earlier. Okay, let's see how it applies to this. Now I'm going to write the partial differential operator. I'm going to write it in terms of tensor product of operators, right? So it's the partial derivative squared, right? Tensor I identity plus identity tensor negative of partial derivative with respect to t squared. Okay, applied twice. If I'm going to apply that technique earlier, I separated into two equations. Okay, now these two equations are both ordinary differential equations. Okay, so presumably you learn how to do that. You can solve them by using whatever technique that you know, and you get the solution. Okay, so it's very nice. Okay, and so now you get a solution that is of this inseparable form. Okay, so how do I get a general solution? I'm going to take a linear combination of this. So it doesn't need to be rank 1. It can be some arbitrary finite rank tensor. Okay, now that gives you the more general solutions. Okay, of course, you can just, there are arguments that's going to allow you to show that this solution gives you everything. Okay, that you have all the solutions, but we don't get that. Now we are actually content with just one solution because even that is very, very difficult when we come to realistic problems. Okay. Now, like I said earlier, now I'm going to give you the details, right? This depends on coordinates. Okay. Now, whether the PDE, right, is solvable, right, or more generally, whether I can write an operator in this form, right? This depends on coordinates. Okay. Now, so, if I just do the simple linear change of coordinates, okay, this is just essentially multiplying xt by the matrix 1, -1, 1, +1, okay, right? It's an invertible matrix, so it's a linear change of coordinates. Now, suddenly I get an operator that is no longer separable, okay? Now, look at this operator. It's a partial derivative respect to xi, tensor product with a partial derivative respect to eta. Now, this is not a separable operator. Remember, a separable operator is not the same thing as a separable function, right? It has to be of the form an operator, tensor product with identity operators in every other coordinate and sum over, okay? Now, however, it doesn't mean that this is difficult to solve, okay? This you can solve this equations quite easily, right? You can see that, this is actually fairly informative too. So the solution to this equation, right, this form of the wave equation is additively separable. Okay, you see that, right? Why? Because when you take partial derivative with respect to xi and eta, and it gives you 0, it must mean that one of the function, right, is independent of xi, the other one is independent of eta, right? It must take this form. Okay. So it's additively separable, which means that if I assume that it's multiplicatively separable, right, it won't work. Okay, so this is the proof that you cannot solve this using the standard separation of variable technique. Okay, now we'll see at the end of our talk, if we do get there, why is this the case? Why is it that this version, right, even though it's exactly the same problem up to a change of variable, can no longer be solved the standard separation of variable technique. It has to do with tensors too, but it has to do with the metric tensors and the Ricci curvature tensor. Okay. Okay, more generally, right, a wave equation doesn't just need to be one-dimensional. It doesn't need to be a string, right? It can be a wave in arbitrary dimensions, okay? So that first d2 by dx squared is actually a Laplacian. Now, of course, I can also apply the change of variable to this case, right? It's exactly the same thing. In this case, this delta here, right, this change, this Laplacian, right, can be in 20 variables if you want. Right, you apply that trick that I taught you, right? Transform a separable system, a homogeneous linear system into eigenvalue problems. Okay. Now this first version here, okay, this first equation here is called the Helmholtz equation. Okay, this is going to be important for us, but maybe not, right? If I don't get that, then maybe not, right? But if we do get that, I'm going to use the Helmholtz equation to illustrate how is it that the metric tensor plays a role in. So there are exactly 11 system of coordinates for which you can solve the Helmholtz equation using separation of variables. Okay, we'll see why that's the case. The solution is also given by, the answer is also given by tensors. Okay, now, okay. Now, let's go back to simple stuff. Let's go back to separation of variables again. Now, so of course, when you learn about separation of variables, you learn about it as a technique for solving PDE, okay? Now, what is the advantage in seeing it in this, my version, this, strange version that's 100% abstract, well, there's no partial differential operators anyway. Well, so the advantage in viewing it this way is that now, all these operators doesn't need to be partial differential operators, right? For example, I could have integral operators, right? Now, this is an example of this is called an integral differential equation. This one in particular, this one comes from heat transfer, okay? So this involves, as you can see, both integration and differentiation. This is not a PDE. However, all you need to remember is that integration with respect to, well, y, right? This is a linear operator, okay? When the limit is given is only in terms of x, okay? Right, so, in this case, right, this is a linear operator. That's all I need to know, right? I can suddenly write it down as a, separable operator, right? Just like before, and I can solve it, okay? Except that in this case, one of this equation is going to involve integration, but it doesn't matter, right? It's integration with respect to x. So I'm just going to take another derivative with respect to x again. Ultimately, I get this becomes a second order ODE. And this is a first order ODE, right? I get this two equation. And again, I can apply standard methods to solve the ODE, right? And get the solution to this weird looking integral differential equations, okay? It doesn't need to be continuous either. You can do discrete, okay? If I do finite difference method, okay? Finite difference method, if you're a numerical analyst, you know what that is. You discretize a differential operator, you're going to get, what are you going to get? You're going to end up with recurrence relation, okay? Now, if you end up with recurrence relation, again, defines a, assuming a linear recurrence relation, defines a linear operator, okay? Right, so phi of k is the operator that takes this discrete variable, can view it as a matrix, right? And does this to it. What is this? This is actually a phi of k, right, is a tridiagonal Toeplitz matrix, okay? And xi is, it's just a matrix that has superdiagonal one and so on and so forth, right? You can view all this as matrices. And again, you can apply separation of variable because phi of k and xi of n are both linear operators. So this abstract technique that I showed you earlier, right, applies, right? So that's the advantage of viewing things abstractly, okay? Right, instead of the calculus version that only applies to PDE. Okay, now again, you can actually solve this in closed form, but that's not important to us. I want to get to the tensor networks. Okay, I already used up half my time. Okay, so the summary is very simple. Okay, if my operator phi is separable, meaning it can be written in this form, this first equation on the top, then it has a multiplicatively separable solution. Okay, that is because eigenvalues always exist over complex. Okay, but anyway, right? So you can write that there is at least one solution that's going to take this separable form, a rank 1 tensor. And by taking linear combinations of this F, right, I get more general solutions, right? I can get a linear combination of this, right? So of course, everything that I'm talking about here, right, says this, okay? That my F, my solution, right, once I get a separable solution, I can take linear combinations to get non-separable, more general solutions, okay? Now, the thing is that, notice that, I use I, right? Each one of this separable term, I'm just going to label it I, and I take a linear combination. Okay, but the thing is, why would I need to do that? Well, I mean, the simplest way, I can give each of this separable term its own index, okay? Now, and then I can index the coefficients by ijk, right? More general solution. These two F are identical, right? These two F are exactly the same, okay? They are both linear combinations of separable solutions, okay? Or rank 1 tensors, if you like. However, because, this technique that I just taught you, it says nothing about how you're going to index your factors, okay? These factors, phi I, psi I, theta I. Or do I index them as phi I, psi j, theta k? Oh, how about I index it as phi I j k and psi j k I and theta k? Well, it doesn't matter, right? It's still a linear combination. You can index this linear combination in any way you like. The indices are completely independent, okay? You can choose them in any way you like. You're still going to get linear combination of, separable functions, okay? And that actually, in my opinion, is what motivates tensor networks, okay? At least, that's the way I would present it. That's the way I'm presenting it, okay? Now, now let's go to tensor networks, okay? It's about, of course, came out in quantum mechanics, so we better review that part of the, background. Okay, so, the thing is, let's start from, in this case, something very similar to the wave equation, right? Okay, it's very similar, except that now I have the imaginary unit, right? Let's ignore all the constants, okay? All these constants, the Planck constant, the mass, all this, let's assume it, let's get rid of all of them, right? It really doesn't matter, right? Just do a rescaling, right? The only thing I can't get rid of is the imaginary unit. Okay, that's important, right? You cannot just change a imaginary number to a real number, okay? So the I has to be kept, okay? We just keep the sign. Negative numbers has to be negative, positive numbers have to be positive, imaginary numbers have to be imaginary. Basically, that's it. Okay, so this last equation here, this is your Schrodinger equation, right? And this this delta, right? They are, this is not one Laplacian. This is like d Laplacian, each for one of your d particles. Let's say you have d particles, okay? Now, I'm not going to assume that your Laplacian is, when I write x, really it's not Cartesian coordinates, it's just some general coordinates. This xi can be, for example, polar coordinates, okay? Okay, good. So now I get this Schrodinger equation, a simplified version of Schrodinger equation. What can I do? Well, actually, what you can do depends on this v here, okay? This real valued function here, okay? Now let's assume that this v here is added. Sorry. Okay. Okay. Sorry. Let me say one thing. Okay. Let's get rid of t first. Okay. Why? You look at this, you notice that this is a radian of the. Okay. Let's assume that v is time independent. Okay. V only depends on the spatial coordinate x. Okay. In which case, it's a radian in the form that allows you to apply separation of variables. Right. It's an operator, right? Tensor product with identity, right? And identity tensor product with another operator, okay? So this is what it looks like. So immediately you can apply separation of variables, right? Because of this abstract technique that we taught. And you separate it into two systems of eigenvalue problems, okay? The second one is an ODE. You can solve it easily, right? It's, the xi of t is just going to be e negative I in t, okay? So this e, because there's only, as remember, right, the constant, the eigenvalues must sum to 0. So if I choose one to be E, the other one must be negative E, okay? Okay, so now that simplifies the problem a little bit, leaving us with the top equation, okay? The top equation is called the time-independent Schrodinger equation. It's an eigenvalue problem, okay? Because you have already applied the separation of variable technique once. So that means you already transform it into an eigenvalue problem. Now I have to solve the first one, okay? That is the difficult part, okay? Now, the thing is, let's try to think of a trivial instance for which we can solve this. Let's assume that the potential is actually additively separable, okay? Now, if the potential V is additively separable, remember what that means? That means it can be written as a sum of functions, each depending on one of the spatial variable, right? There are D particles, each one has its own spatial coordinate, and V, the potential is going to be dependent on all particles, but let's assume that you can just write it as sum of potential, each depending on only one particle. Now, in that case, you can immediately transform the time-independent Schrodinger equation into the form that we need, okay? What is the form that we need? The form that we need is exactly the form that can be solved using separation of variables, okay? You can write it in this form where the operator is separable, and you immediately transform it into D ordinary differential equations that you can solve, okay? Each one of these you can solve easily. So what does this toy example tell you? This toy example tells you that if the potential is additively separable, then the eigenfunction is multiplicatively separable, and the eigenvalue, right, actually this just says that, the eigenvalues must sum up to 0, and therefore it must be additively separable, okay? So this allows you to take a D particle system and break it down into D one particle system, separation of variable, okay? Now, obviously, it cannot be so simple, right? This is useless, okay? This is unrealistic. When you say that the potential is a sum of, it's additively separable, that just says that the particles do not interact. Obviously, that's not going to be the case, right? Electrons are going to interact with each other. Protons are going to interact with, particles in general, they interact, okay? Now, so let's go a little bit up, okay? Let's assume that they only interact with one other particle, okay? Let's simplify this enormously. Of course, every particle is going to interact with every other particle, right? Okay? However, let's simplify things. Okay, let's just look at the next most general case. Instead of just saying that everything is a sum, let's allow pairwise interaction. So now the potential is going to have a ij term that talk about interaction between particle I and particle j. Okay, but there's nothing that's of higher order. Okay, I can even make this very, very simple. I can just assume that the potential is just the, reciprocal of the distance, okay, between particle I and particle j. Even this extremely, extremely simple scenario, it makes the problem intractable. And intractable in the worst possible way, okay? Now, I don't even have to talk about exact solution. Let's talk about some of the most common approximation technique. Okay, Hartree-Fock, we're going to look at that. Hartree-Fock is NP-hard, okay? Even if I just assume a pairwise interaction where the potential has this simple form. Okay, Hartree-Fock, meaning you find a rank 1 separable approximation to a solution that's already NP-hard. Okay, now density functional theory, right? It's a more sophisticated version, right? Or approximation theory. They're trying to find approximate solution. That is what's called QMA hard. Okay, quantum Arthur-Merlin or quantum Merlin-Arthur hard. That means even if you have a quantum computer, right? A quantum computer will not be able to solve this in polynomial time, assuming that all this hierarchy is as the computer scientist expects. Okay, so this results of Norbert Schuch and Frank Verstraete. Okay, what's an amazing result, right? Even approximation is already hard, and even under such strong assumptions. As soon as you go beyond this unrealistic, right, regime, right, where your potential is additively separable, you immediately get into this saying that they're pairwise separable, okay? But that already brings you into some of the most intractable regime. Okay, so like all these approximation techniques, including tensor network, would be essentially approximations, okay? And it's based on this very simple heuristic, okay? Now, what we know, and what I said earlier, is that if my potential, right, is additively separable, then my solution, right, my eigenfunctions, is multiplicatively separable. That's exactly what, the separation of variable techniques does, okay? The version that I introduced, okay? Now, what approximation is saying that if it's approximately, if it's approximately, the potential is approximately separable, then the eigenfunctions, right, must be approximately multiplicatively separable. Okay, that's sort of well, the way I see it, okay, from like 1,000 yards away, right? This is what goes on between like all these different types of approximation schemes in computational quantum chemistry, computational quantum physics. Okay, they're all based on these ideas, right? So the thing is, I am not going to go into this. Okay, so let me just quickly say a word about Hartree-Fock. Hartree-Fock essentially is saying that I'm going to find, well, I know that my solution is not going to be a rank 1 tensor, okay? It's not going to be multiplicatively separable. But let's try to find the best rank 1 approximation. Let's try to find the best rank 1 phi that approximate this, okay? Now, the thing is that problem is NP hard, okay? The thing is, why? The thing is, even if you discretize everything, you're going to get a quadratic programming problem on a Grassmannian. Okay, the set of well, even if you like, if you add this altered, okay, forget it. I won't say anything about that. Okay, but let's add more information. Okay, let's assume that so Hartree-Fock, some people just say that I'm just going to find the best rank 1 approximation. That's Hartree-Fock. But actually, if you look at the original paper, it contains a little bit more. Okay, it actually brings in some other information, right? And under those, assumption, you can actually get, roughly speaking, right? You make some simplifying assumption. Okay. Ultimately, you're gonna get a system like this. Well, what is this? This is again, right, a eigenvalue problem, right? Like I said earlier, right? If I assume that the potential is approximately additively separable, then the solution is approximately multiplicatively separable. So this sort of attests to that, okay? Now, except that in this case, the operator actually depends on other particles, okay? This J, this phi J here, this is the eigenfunction of another operator. Okay, so this is actually not quite your eigenvalue problem. Okay, it's not as simple, right? But it has that form, you see? Right? It has that form, right? It has some linear operator, or except or linear depending, well, it's up to sort of, it's debatable, okay? Because it depends on phi of J times phi of I equals lambda I phi of I. So it does have that eigenvalue problem form, okay? Okay, but anyway, right? So this is Hartree-Fock. This is sort of a standard way to deal with this lack of this thing, right? This problem that you don't really have a additively separable potential. Okay, so what if I assume that it's not rank 1? That's actually, there's something called a multi-configuration Hartree-Fock. Well, ultimately, you're going to look something that looks a little bit like an eigenvalue problem too. I won't go into that. Okay, right? So, except that your eigenvalue now is going to be a matrix, okay? The eigenvalue is no longer a scalar, it's a matrix. So, but it also does look like an eigenvalue problem, okay? So, it sort of, attests to my point that if you assume separability, approximate separability, you're going to get something that looks almost like an eigenvalue problem, okay? Now I'm going to talk about tensor networks, okay? Now, so tensor network, like I said, right, in my world, well, the way I view it is that it is yet another way to approximate this separation of variable techniques. Okay, remember that ultimately, at the end of this separation of variable techniques, assuming that everything goes through, at the end, you get a rank 1 solution. Okay, you get a separable solution. That's the whole point, right? You assume that the solution is separable. And then to get a general solution, you're going to take linear combination of separable solutions. Okay, So this is what you assume, right? There's the most general way is to give each of your separable, each of your factor a different index, and you take a sum like this, okay? Now you can even, well, the good thing about this is you can even assume that each of this phi I, right, forms a orthonormal basis, right? That's the advantage of giving every copy of the factor its own index, okay? Now, however, what is a problem here is that the Cijk explodes, okay? The Cijk has, let's assume that all this number of summons are the same, they're all R. Then how many summons are there? It's R to the D summons, okay? So which means that, let's even assume that R is equals to 2, okay? So there are 2 to the D terms. And so you have a system with 1 mole of particles, okay? Then this problem becomes undoable, okay? So, however, the motivation is that I don't need this. Like I said, each copy of this can be given any index that I like, okay? Okay, no, actually, the thing is, let me actually take a step back. I won't go there right away. Let's think about how I can reduce this space, okay? Now I have to look at the space of all, let's assume that this phi and xi and theta, all these factors are already found, right? You apply separation of variables, right? Each one of this is a solution to an ODE, and let's assume I can solve all this ODE. So all this are already known. What is unknown is this Cijk, okay? This coefficient. And there are R to the D of them, okay? How do I simplify that? One way is to assume that this thing, right, this coefficient itself comes from something of, it has a form, okay? It has a form. So what's one way to give it, I'm going to assume that Cijk, right, is the trace of products of matrices, okay? Now, how many possible Cijk are there? There are R to the D of that, right? Okay, but how many possible matrices are here, right? There are only D possible matrices that you can put here, right? And each, of course, depends on an I, but ultimately, instead of having R to the D, degrees of freedom, now I have R times D times n squared for each of this matrix, okay? Let's assume that they're all of the same dimension. Okay, so this is a way to reduce the structure. That's the way I see it, okay? Of course, in physics, okay, if you look at this original papers by White, okay, Steve White, and of course, the famous AKLT paper, there are good physics reasons, there are good physical reasons to assume that the coefficient actually has this form, okay? That's probably the physicists in the audience, right? You should ask them, not me. Why is it that this is a good ansatz for the coefficients, okay? Now, the thing is, actually, the word ansatz tends to be used for this, the function itself, where the coefficient Cijk actually is assumed to have a form like this. Okay, so instead of R to the D possible values, right, I just need to find R, D, n squared possible values for these matrices, okay? Now, this is called the matrix product state, obviously, because, it's from our matrix products. Okay, this is called an MPS, okay? Matrix product state, the best known tensor network, okay? Now, let's look at the simplest possible case, okay? Now, let's look at a case where AI is a vector, okay? N1 is equals to 1. AI is a row vector. And CK, the last term here, is a column vector, okay? Now, if the first AI is a row vector and the last CK is a column vector, what do I get? No matter how many matrices you have in the middle, this thing becomes a scalar, okay? So trace of a scalar is itself, so you can even drop the trace, okay? Now, this is the simplest kind of MPS, and it's called MPS with special, with open boundary conditions, right? If you can even assume that AK and CK, I think this is what I said, right? Well, actually, I take that back, okay? Yeah, okay, so I cannot remember what's the one with, yeah, so I'll take that back. Okay, so the thing is, there's a gap in my memory. Okay, but anyway, let me just say this, okay? Okay, good. So, other things, right? You can assume that the matrices AI, BJ, CK, right, are all in SVD form. Okay, then that means I can combine the left and right matrices, right? I can actually even reduce I can even reduce the dimension of this problem further. Okay, this AI, BJ, and CK, all these matrices can be assumed to be in already SVD form, okay? And you can actually even reduce the parameter space. Okay, but anyway, right? Now, this is, of course, what I view as the original motivation for tensor network. It's a way for you to reduce the dimension space of this coefficients, okay? However, there is a structure, okay? There is a very important structure that's going to lead you to more esoteric, more general tensor networks, okay? What is that? Now let's actually take the d=3 case, okay? Let's say there's only ABC, right? I'm no longer putting dots in the middle, okay? Now I actually have the trace of the product of 3 matrices, right, as the coefficients. Now I'm going to expand this, right, expand this, right, and ultimately, right, each of these matrices has its own indices, right? If you expand it, ultimately you realize that everything sums over, right? And you can write it in this form. You can again write the same f, right? Instead of a linear combination of separable terms in the indices I, j, and k, now it becomes a sum of separable terms, right? It's a linear combination, if you like, in indices, but these indices are now different. Alpha, beta, beta, gamma, and gamma, alpha. Notice that the indices are now dependent, right? The first 2 factor has the same shares one index. The second and the last factor shares another index, and the last and the first factor shares the first one. And this is simply by taking the MPS ansatz and expanding it. Okay, now let's draw this. Okay, what does it look like? It looks like a triangle, right? Now, if I draw this structure, what is this? It's a triangle. It's the simplest undirected graph. Now, the thing is that if you think carefully about it, I can actually write down given any graph, I can write down a sum of separable functions indexed by that graph, where the indices are the labels are the edges. Okay. Now, so this actually gives us all possible tensor networks, including ones that are not ever proposed. Okay. So if you look at any tensor network, the thing is that there is one that I actually cannot put in this form. But anyway, right? Most tensor networks, okay, well, they look like this, right? And if you look carefully at the index structure, you realize that they are simply graphs, okay? They are simply graphs. It tells you which 2 factors share an index, okay? So take any graph, right? Let's say I am looking for, a problem with 5 variables, right? 5 particles, u, x, x through w, right? And then the thing is, I'm going to form a rank 1 tensor or a separable term in this manner. I'm going to label them in the way with indices, but these indices would have to form a graph structure. For instance, phi and xi would share the index j, okay? Now that's the last one here, okay? Phi and xi would share the index j, okay? See this index here, okay? And, xi and rho and theta, would share would share k and l, right? Oh, sorry. How come? Yeah, here, right here. Okay. Yeah, so we share k and l, right? Xi share k and l, k with rho, right? And l with theta, right? So the thing is, if you already know, right, this is obvious, right? If you do not already know this, right, you have to stare at it for a little bit, okay? But it's a very simple structure. So tensor network, right, at least, in my perspective, is simply a way for you to play with the index structure of a sum of separable functions. Okay, that's it. That's the relation with separation of variable. The separation of variable technique gives you a separable solution. Okay, rank 1 solution. Now it doesn't say anything about the index structure. Okay, if I take a sum, I get a general solution, but it doesn't. There is no index, right? It doesn't say anything about indices of your separable terms. Now, tensor network is a way for you to impose a graph structure on the indices, and by so doing, you actually reduce the space of, right, instead of looking at all possible linear combination of separable functions, I'm just going to look at a very small subset where the index structure, can be labeled by that graph. Okay, that's it. Okay, that to me is tensor network. Okay, I only know one tensor network that cannot be formulated in this manner. Okay, but everything else, well, basically this is it, right? And since this is a first course, I think it's enough. Okay, right? I think I tell you about 90% of all the possible tensor networks out there using this framework. Okay, good. So, well, I'm not sure. Do I have time? It's
Yes,
5 minutes to.
Yeah, you still have 5 minutes.
I have 5 minutes. Okay, so in that case, let me go back to separation of variables. Okay, now, and I would also go back to tensor networks too at the end of this. Like I told you, okay, let's look at the Helmholtz equation again. Well, you can look at Schrödinger equation, doesn't matter. Like, let's take any equation, but this is easier. I'm going to look at this one, okay? Now, so, like I told you earlier, right, separation of variables ultimately depends on coordinates. Now, if I take this in terms of Cartesian coordinate, the standard one, and apply separation of variable, it works, okay? Now, if I apply polar coordinates, I change it to polar coordinates, right? A Laplacian would take a different form, right? I apply separation of variables. It also works, and both give me interesting solution, okay? Right, it tells me features of the solutions that are otherwise not discernible from the other one. Like for instance, the second one actually gives you Bessel functions, okay? Now, for this two variable, right, this is a Helmholtz equation in two variables. There are exactly 4 systems of separable coordinates. There are no others, okay? The 4 system, right? Cartesian, polar, which I showed here, and parabolic and elliptic, which I didn't. Okay? For n equals 3, okay? Now, so this is, of course, 2 variables, right? X and Y, right? Or R and theta, right? If I do 3 variables, right? X, Y, Z, or X, Y, Z, or R and R theta phi, or, depending on what coordinates you want to give it, they're exactly 11, right? I mentioned this to you earlier, right? 11 different coordinate systems for which you can apply separation of variables, okay? Now, how do I know this, okay? Now, there is some very interesting mathematics, but behind this, unfortunately, I think it's largely forgotten. If anybody knows this, right, let me know, and in case I would know that I'm wrong, right, but most people I talk to doesn't know about this. It's called the Steckel condition, okay? Probably it's not pronounced Steckel because there are 2 dots on the A, so it's pronounced something else, but let's say Steckel condition. Well, Steckel condition says this, okay, that a PDE, right? Okay, in this case, it's just Helmholtz equation, right? But in general, any PDE, any semi-linear PDE, can be solved using the separation of variable technique if and only if, so this is necessary and sufficient, if the metric tensor G, okay? Now, every coordinate system, right, a metric tensor, right, of course, from for X, Y, Z, right, for Cartesian, metric tensor is just an identity matrix, right, at every point, right? But you have polar coordinates, well, even though you're still on flat space, right, still in Rn, right, R2 here, R2 or R3, your metric tensor becomes a non-trivial thing, okay? It becomes a matrix whose coordinates depends on R and theta, okay? Now, if that matrix, that metric tensor is a diagonal matrix, okay? It doesn't need to be a constant matrix, right? Of course, if it's Cartesian, it's always going to be identity, it's constant, but in general, it just needs to be a diagonal matrix. That is a necessary condition for application of separation of variables. And the second condition is a little bit more mysterious. This is the Steckel condition I was talking about, right? It says that if I take this diagonal matrix, what is this diagonal matrix? The diagonal matrix, the first condition says that the metric tensor must be a diagonal matrix, okay? Okay, in this coordinate system. Now, what is this? These diagonal entries cannot be arbitrary. Of course, they have to be all non-zero functions, right? And more than that, they have to be this G1, this diagonal entries have to be of this form, okay? If I take, it must come from a matrix like this, okay? This S matrix, this is called a Steckel matrix. Now, this matrix is unusual in that the first column, the first row depends only on the first variable, the second row depends only on the second variable, and the nth row depends only on the nth variable. Now, if I take the inverse of this matrix, it's no longer going to have this property, right? If I take the inverse of a matrix like this, every entry is going to be mixed up, right? So you're going to have every entry is now going to depend on every other most entries in the matrix, right? If I take a look at that and I look at again at the first row, okay, I look at the first row of the inverse of this Stekel matrix. If that happens to be exactly the inverse, right, the reciprocal of G11 to Gn, then this is, say, this that satisfies the Stekel condition, okay? Okay, note that the diagonal of this, this is a metric tensor, right? So it must be, or this must all be non-zero functions, right? So 1 over Gjj must be equals to the first row of the inverse of this matrix, okay? Of a matrix of this form. That is the Stekel condition, okay? Now, if it satisfies both these conditions, then that solution, that PDE can be solved using separation of variable technique. Well, here I said Helmholtz equation, but it can be generalized, okay? It can be generalized to any semi-linear PDE, okay? Now, let me give you one last example, right? Like I said, if it's, let's look at Helmholtz equation for in 3 variables. Well, if I look at Cartesian coordinate, then obviously the metric tensor is just identity. But if I look at some other coordinate, let's say spherical coordinate, right? The metric tensor is going to look like this. 1 r squared sine squared theta, right? It happens to be a diagonal matrix, right? In general, it doesn't need to be. But for spherical coordinates, it is, in fact, a diagonal matrix, okay? So it tells me, well, there's a chance that you can use the separation of variables to get a solution. And turns out you can. Why? Because, if you look at forget about the other terms, just look at this one, okay? 1 r squared sine squared theta. This happens to be the reciprocal of the first row of this matrix S, okay? This inverse of this matrix, okay? So that tells you it satisfies the Stekel condition, which means that I can solve it using separation of variables, okay? Now, the thing is, this condition, I have been trying to understand what it is, okay? So the thing is, I know there are great algebraists around here, right? I just saw Giorgio on the screen, but it's gone now. I'm hoping somebody can tell me what that condition is, this second condition is, okay? And more generally, I would like to know, forget about that, right? I would like to know what are the Stekel conditions for tensor networks, okay? How would I know whether a PDE can be solved exactly, right, with a tensor network ansatz? In particular, let's say I'm content you can do it for MPS, okay, matrix product state, the simplest tensor network. What is the equivalent of Stekel condition for tensor network? Okay, I'm going to leave you with this open problem, right? Hopefully, somebody will get back to me. I have a question, right? What exactly is this Stekel condition? Well, some algebraists might be able to tell me. And the second thing is what this is an open problem. I do not know. Okay, this is a problem, right? What is the equivalent of a Stekel condition for MPS? Okay, or more generally, any tensor network. Okay. So thank you very much, right? So a lot of this material, right, is joined with Koyet, and some of this more elementary stuff, it's in my book chapter in Uptime America. Okay, thank you very much.
Many thanks, Lek Heng. Other questions from the audience? Oh, plenty. So.
Okay, thanks. You can hear me? Can you hear me?
Yes. Loud and clear.
Okay, perfect. Thanks for the talk. This was very interesting. I just have a question because if you come from, let's say, condensed matter physics and you use MPS for various reasons, mostly ground state computations, then there's the notion that what you actually do with an MPS is you focus into a corner of the Hilbert space. You restrict your Hilbert space, and this is very strictly motivated by sort of entropy arguments and correlation arguments, whereas here it's not very clear what the motivation of this ansatz, because we're not, this is not longer a restriction to a Hilbert space, but some other space. So what is the motivation behind doing this? Is there also some kind of notion of corner of the Hilbert space?
Exactly. The thing is, this is exactly, addressing that, when I said, remember, if I take any two, right? If I take any two, let's say any two functions of this form, I add it, right? It may not take this form, right? So this is it's not a subspace. It is exactly a corner. Each of this tensor network that I wrote here that can be parameterized as a sum of separable functions indexed by a graph. This parameterizes a small subset, okay, a corner of a Hilbert space, okay? It's not a subspace, right? Because it's not a closed under linear combination, okay? So this is my way of describing that subspace, that subset, right? When you look at that subset of all the tensor network that can be parameterized as, a triangle, let's say, okay? That is one tiny corner of the Hilbert space of all possible solutions. All possible solution meaning all possible sums of separable functions, okay? I am just looking at the set of all sum of separable function whose index structure obeys this conform to this graph, okay? So, I'm just describing it in a different way. I'm describing this little, I saw that picture too, okay? In fact, I reproduced that picture for my own paper, okay? That you have this, huge set, right? That denotes all possible solution in an entire Hilbert space, and you have some little blob that is just the set of where the solution is likely to lie, okay? And so, well, of course, in physics, condensed matter physics, that set is selected by physical intuition, right? For me, it's given by a graph, okay? You pick a graph, and that graph defines one tiny corner. I shouldn't say corner, one tiny area inside your entire Hilbert space. And, well, that is where your solution is going to lie, right? At least according to your physical intuition. For me, what is that little corner? That little corner is exactly the set of all functions that can be described as a sum of separable function whose index structure has a graph like this, conforms to a graph like this. Okay?
Thanks.
Thank you.
Hello.
Yes.
Hi. Thanks for the talk. Just a small question, I guess, related to this page as well as the common examples page. So when you wrote down your tensors, all your indices were all down. So the question is whether covariant or contravariant character of your indices, does that play any role, I guess, in the description of these tensor networks, as well as, and if so, is that encoded in these associated graphs at all?
Yeah. So no. The thing is, my indices are always going to be subscript, right? I don't use the Einstein summation convention because, well, I guess it's sort of in a LaTeX, generation, right? You can type a summation symbol fairly easily, right? So there's no, I want to specify exactly which indices I'm summing over, right? So yes, but if you look at the indices, right? What I'm saying here is that the factors, okay, the factors are labeled by Greek letters. Well, those are the function, right? Phi, xi, theta, right? The indices are the lowercase Roman IJK, right, and so forth, right? And the thing is, the factors, right, the Greek letters are the vertices, right? The Greeks, the Roman letters are the edges. Okay, basically this is it. Okay, Greek are the factors, and it tells you which two functions, right, which two factors, right, shares an index, okay? Theta and xi shares an index. Theta and phi shares an index. Xi and phi shares an index, okay? And if you look at that, that's exactly what's going on here, right? Phi and xi shares the index j. Xi and theta shares the index k, and theta and phi shares the index I, okay? So that is, this I understand, this is probably not the way you would write it, okay? And the thing is that, this is probably not the way that you would write, you would show a tensor network, okay? But this is my way of distilling it for myself, okay? Okay, that's, sorry for the idiosyncrasy.
No, it's fine. Thank you.
There are a few more questions. Please hold on.
Go ahead.
Okay, so thank you for the talk. I was wondering earlier you talked about the best rank 1 approximation.
Yes.
So this is of a given function and you want to approximate it with a simple separable function, right?
Yes, yes.
So what's the technique to do
No,
it?
I didn't do that, right? You know, I was telling you that even this is already very hard, okay? Like if I, let's say, right, you know, if I want to, let me see, yes, okay? Let's say I want to find a solution that has a form like this, okay? Now, the thing is, this is difficult, okay? Rank 1 approximation is difficult. Now, I can introduce some structure. First, for instance, right, let's say, you know, if I know that I have fermions, okay? If I have fermions, then this tensor product becomes, well, you know, an alternating tensor product, okay? It becomes wedge. All times becomes wedge. So it should be easier, okay? Now, the thing is, it's also not easier, okay? Because it's like, you know, I was trying to get at that, okay? Like, you get a quadratic optimization problem over a Grassmannian, okay? That's alternating rank 1 tensor. That problem is NP-hard, okay? Now, let's put in even more information. Let's put in information like, well, you know, the solution must be solution to this Rayleigh quotient, must be like a stationary point of this Rayleigh quotient, right? If you add that as so the more information you give it, it makes it easier, right? But even if I give it all this information, like all these factors, this solution must be a critical point of your Rayleigh quotient. This problem, like, is Hartree-Fock approximation. This problem, according to the results that I presented here, okay, Schut and Verstraete, is also NP-hard. Okay, so finding a rank 1 approximation of a tensor, even a finite dimension tensor, this is already NP-hard, right? Even if you impose additional structure, like let's say you have an alternating tensor instead of a general tensor, that's also NP-hard. Okay, if you assume things like, oh, you know, my rank 1 tensor is the solution, is a critical point of the Rayleigh quotient, right? This is incorporating like physical information. This is also NP-hard. So every variant of this rank 1 approximation idea is NP-hard. So if you care about computational complexity, then, you know, to me, this is intractable, okay? Right, of course, you know, all you care is about running some MATLAB experiment, then, you know, of course, you know, this is fine, right? But if you care about computational complexity, then, you know, it actually says that none of this method are tractable, right?
Okay, thank you.
Other questions? I have one regarding the computation of these matrices for the MPS. You mentioned some singular value decomposition. Can you explain this a little bit more, please?
Oh, yeah. So the general form of MPS takes this form, right? You have basically matrices, right? Each of these coefficients is the trace of a product of a number of matrices. Let's say 3, okay? A, B, and C, okay? Right, so each F can be written as a trace of AI, BJ, CK, and you have a collection of matrices A1 to AR1, B1 to BR2, and C1 to CR3. Okay. Now the thing is, when each one of these matrices has n square coordinates, how can I simplify this? One way is to say that instead of writing this as AI, I'm going to assume that AI is already in singular value decomposed form, meaning that AI is already written in the form U sigma V transpose. Okay, now the thing, what's the advantage here? The advantage is that the UI and the V of the next factor can be combined into a single orthogonal matrix, so that now I simplified it. I can just write an MPS, the coefficient of MPS, I can always write it in this form. It's an alternating product of orthogonal matrices or unitary matrices with diagonal matrices, okay? If I do that, you know, I reduce the number of parameters even further, okay? From a collection of matrices to a collection of unitary and diagonal matrices. Okay, so that simplifies things by a little bit. Okay.
Okay, thank you. Thank you. Other questions before we finish his first talk. Oh, yes, there is one up there. Yeah. Another question coming.
Sure.
Oh, hi, nice. Thanks for the nice talk.
Thank you.
One question. So I'm very curious about, you mentioned that you know one tensor network that cannot be expressed in the form that you had at the end. So
Yes.
which one is that?
Yeah, so that's called MERA, M-E-R-A. But so that involves
That's what I
certain
imagined.
features, that cannot be captured using this framework that I introduced. Okay, so essentially, if you drop that, then every tensor network that I know of can be written in this form. Okay, that it is a sum of separable function whose index structure forms a graph. That's it. Okay. Now I guess MERA has some other features that cannot be put in this form, right? Basically, that's the thing, right? So if a mathematician is going to define tensor network, then MERA is not a tensor network, okay? But of course, it's not up to us, okay? I understand, right? It's whatever physicists insist, okay? Yes.
Okay. Many thanks again, Lek Heng, for a nice talk.
Well, enjoy the rest of the talk. Well, sorry I can join you. And thank you for having me.
And so we'll have a 15-minute break now before a session on tensor networks. So thank you and goodbye, Lek Heng.